Greetings, Earth scientists, and we are here today to learn about weather disasters. We'll be looking at thunderstorms, tornadoes, and hurricanes. Then we'll take a break, come back, and actually learn about specific cases that are important to history where weather disasters are concerned. Now, thunderstorms don't just pop up for no reason. They actually require several things to occur. A moist and warm air parcel. So those air masses we were learning about and air pressure play a role in development of thunderstorms. You must have instability of that air mass where you can have lifting of the air mass so it will constantly go through a convection process. Typically, the ground must have a pretty warm surface temperature that helps aid in what's called latent heat of condensation. And that's why your storms are most common in the late afternoon, early evening time frames when the ground has had enough time to warm. So you get a couple of development of thunderstorms when they occur. They go through stages. The first one is a towering cumulus, and that requires a continuous supply of warm air and moisture. Each process or surge of that moisture and warmness causes the air to rise higher because warm air rises, and updrafts and downdrafts occur. This is also where you can start to develop hail balls. At a full maturity stage where a thunderstorm has reached its peak, the precipitation forms, and this is the most active and dangerous stage of a thunderstorm because this is when you'll probably see your electrical storm, hail that may fall from the sky, sideline winds, wall clouds, things of that nature. In the dissipating stage, a thunderstorm actually has a cooling effect of the air and the precipitation that it produces when it finally reaches its dew point. The whole system begins to cool down and eventually dissipates the energy out. So when you look at the three stages of the thunderstorm, you get the first stage, which is the cumulus development. Notice you only have updrafts here of rising of warm air. Now in the mature stage, you have warm air rising, cool air sinking. So that's going to create more of this process right here, convection. At the dissipating stage, the anvil has already formed and it's only producing light rain. This is the stage we need to be most worried about in terms of risk of thunderstorm dangers. So when you see a towering cumulus like this, the hard cauliflower appearance that you see shows that there's high energy levels, high moisture, high heat in that system, and it's growing at a fairly rapid pace. I even see a hint of green in here. That should be an indicator that you're going to have probably hail come out of that storm. So if you ever see clouds turn green, that is an indicator to get to safety because little bitty hail doesn't seem like such a big deal. But I have actually lost a car to softball size hail, and I can tell you they're absolutely scary if you're out without protection in that kind of a hailstorm. Here's a mature thunderstorm that's ready to rock and roll, ready to give its thing, and I would be very cautious of one like this because especially if it turned dark colors and a green color, that would be your indicator it's probably fixing to go. Notice that you just have light rain occurring in this thunderstorm. It used to be a lot bigger, probably more like this, and now it's dissipated its energy and it's collapsing, and eventually it'll fizzle completely out. So what are the features of thunderstorms? Typically you'll get heavy rainfall. If it's lots of energy and electricity, you'll end up with an electrical storm. Those are some of the most beautiful thunderstorms, but very dangerous. If you do get hail, keep in mind the longer that storms had a chance to get those updrafts and downburst, the more rotation that hail ball has been through, so the more layers that it's going to develop. At any given time, there's approximately 2,000 thunderstorms in progress somewhere on the planet. We have about 100,000 of those a year in the United States, with the most frequent areas for thunderstorms being in Florida and the eastern Gulf Coast regions, and partly because you get warm, moist air off the Gulf of Mexico and fairly warm ground surfaces. So when you look at that, does that totally ring true with what we just talked about? You can see Florida has the home run here for being the most intense on thunderstorms. And then you see in this section quite a bit of them. Notice that comes down through eastern Texas. We're not too far off the mark in the 40-ish area right here. But let me point out, this section right in here is Tornado Alley. So never underestimate the fact that the number of days that you could have thunderstorms on any given day, we could produce a tornado in any of those storms. This would be a major thunderstorm that's produced a supercell, which is multiple thunderstorms that have begun to rotate together. These are pretty dangerous things. You can see a big giant wall cloud right here. This would be where I would start looking for, especially in this area, a tail to fall to create a tornado. This is a supercell tornado, tornadic thunderstorm that you can see rotation in Minnesota. And you can see that rotation very clearly. It almost looks like a hurricane, doesn't it? So some of these thunderstorms actually have characteristics of hurricanes that are very large. They just don't move in from the ocean. So let's look at tornadoes next. Tornadoes are a vortex of air that have been moving at a certain mile per hour and higher. Not all tornadoes behave the same, but tornadoes have devastating impacts because they can pretty much eat anything in their path if they're pretty strong, which would be an F4 or an F5. We're going to look at that Vegeta scale in just a second. Typically, tornadoes are short-lived. First of all, let's look at the clouds in the background. Do you notice that they kind of have that green tint? Well, that should be one of those clues, red flag, we need to get to safety. In addition, if you start to get those sideline winds and you start to get downburst and downdrafts that really are incredibly strong, you do not need to be in a mobile home. You do not need to be on foot outside. You need to get somewhere that has some kind of secure top to it that if it blew off, you'd still stand a chance. Your best place is to get in a storm shelter. Not all of us have that, but in Tornado Alley, if you build a house, it's a super wise idea to have a tornado shelter, a storm shelter. So when you get a tornado, it's a violent windstorm where the column of air is extending down from a cumulus nimbus cloud and that's producing a vortex. It's a low pressure system inside the air that causes it to rush inward. Because remember learning about millibars, and the lower the millibar reading, the more dangerous the air mass? Well, that's certainly the case here. You can get winds that approach 300 miles an hour with a tornado. The smaller suction vortexes can form inside strong tornadoes, and you can get multiple vortexes within one tornado where it starts to drop many of them together, and they can become very dangerous. So here's a suction vortex right here. That's what I was talking about. Here's the tornado main vortex right here, and here's your suction vortex. And this suction material literally can suck material right off the ground, even large, heavy things. So here's a supercell that's produced a tornado. You can see it coming down right here. Here's that wall cloud. One of the things to always be looking for. And you see that rotation, and it's finally released that, and it's coming down and creating a tornado at the surface. So you might go, oh, well, that's just really cool. That's just wind-blown debris. Let me tell you a little bit about the wind-blown debris. This would be a great test question. First of all, the wind was so high during this tornado that it shook the phone pole and actually loosened up the atoms in the phone pole. So when this metal sheet material came through, it hit it, but because it was already, the wood was already loose, it shot through it, and as soon as the storm was over, it let it go back to its normal atom sitting. So while tornadoes can create piercing damage just like this in a hurricane or in a tornado, this is actually fairly common that you'll see from leftover storm debris that gets captured in stuff like houses, phone poles, cars, and so forth, where it was wedged in something very solid because of the speed of the winds. Now, on average, 770 tornadoes occur in the United States in terms of developing that will actually turn into a storm that we need to be concerned about. The most frequent time frame is April through June, because remember, there was a lot more thunderstorms than there are tornadoes. We're not exactly 100% sure how they form. We're trying to learn that. That's part of the idea of climate modeling, of tornado modeling. But we know whenever there's a mesocyclone present, there's about a 25% chance of a tornado forming. So we're going to look at mesocyclones and show you how they form. You get spinning winds along the side of the ground here, and because you get sideline winds. That's one of the key things of forming a mesocyclone. And what will happen is some of that warm air from the ground will push that sideline winds upwards and start to make a vertical rotation of a cloud. That's when you get into the mesocyclone point. When you get that mesocyclone and you've got that energy moving vertically like this, you're going to start to get a rotation of an air mass. So like on something such as Doppler radar, we're constantly looking for the mesocyclone development and then a tail to form right here to show where we need to be creating and issuing thunderstorm warnings and tornado warnings and watches. So this is actually in Waco, Texas. I actually lived here and was in this particular tornadic event. And I was actually in this building right here on the 5th floor. I was an RA and that building. And I want you first of all to look at the wall. Can you see the wall cloud? And then you can see that there's some, looks like there may be some really dark green and grayish black color. I'd be concerned in this entire area right here that we would get, especially this section right here, that we would have a tail drop. This was a scary storm. This is the one that ate my car, and along with hundreds of other people's on campus, and it ruined buildings all over Baylor University when that occurred, because these were at least softball size hail balls. People who were running that afternoon, if they didn't seek shelter, they made it to the emergency room because it was amazing they lived if they got smashed by some of these balls that were that huge. So conditions for the formation of a tornado have to be just right. They occur usually along the edge of a cold front. Sometimes we'll get them just at the beginning of spring, but typically it's in your true spring months such as April and then May, and associated with even through the summer when you get really warm air masses that are moist. And so if you get those conditions, then you're going to get thunderstorms developing and sometimes even supercells, which again is multiple thunderstorm cells rotating together. So the characteristics of a tornado are a couple of things. The diameter can be anywhere between just a quarter of a mile to a mile or more wide. The speed across the landscape that they can travel literally can be about 30 miles an hour. So these things can travel very quickly with very little time for people to get to safety. And the damage path that they'll eat, they can literally cut about a 6-mile long path, sometimes longer, depending on the duration and the intensity of a tornado. Some might not actually create any damage at all. But some of these very devastating F4s and F5 type tornadoes can create massive damage. When you start to look at the tornado incidences per 10,000 square miles for a 27-year period, I want you to take a look at Tornado Alley, which we sit right smack dab in the middle if you're in Central Texas, North Texas, even parts of South Texas. So you need to take a look at Oklahoma, northern parts of Texas, the Panhandle, Central Texas, all the way up through the Plain States here. These are high occurrence of tornado areas. It doesn't mean you cannot have a tornado anywhere. Certainly can, just the frequency is not as common as what you would see right in this area right here. So I want you to kind of look at an area over a 50-year period of time in Illinois, and all the black dots represent areas that had a beginning point of a tornado. And then you can kind of see that the tornado aloft is in blue, and then the tornado track on the ground was in red. And what I'm wanting you to look at is the direction of the arrows and see if there's any systematic development and planning that we could have done for these people? Does it kind of look like it primarily moves from one side to like left to right or right to left? Does it kind of look like that to you, or north to south, south to north? That's something important to notice about characteristics of storms. Now, let's talk about forecasting tornadoes. First of all, tornado watches are alerted when there's the right conditions to form a tornado, but one has not been spotted or tracked on the ground or by Doppler radar. So literally, when they're issued, we issue them over the course of a 65,000 square mile or square kilometer, area. So that's 25,000 square miles. That's a pretty large surface area that we'll be watching for thunderstorms to develop. If you make it to a tornado warning, most of you already know this. One's already been spotted or sighted or indicated by weather radar. But one of the things we're really looking for is the use of Doppler radar has rapidly changed how we can give warnings, because look at this right here. Do y'all see this little bitty tail right here? I would be concerned that would be a tornado. It's a circulating air mass. We have a mesocyclone, and this one's producing a tail that could drop. So likely this will produce a tornado right here if it has not already. Most of the tornadoes move towards the northeast, which is exactly kind of what you saw in the Illinois picture. And maximum range winds can literally be about 310 miles an hour. That's pretty incredible. The Fujita intensity scale is how we measure tornadoes. So there's a similar scale for hurricanes. Different process, but we'll learn each, and you're going to need to know each for your test. On the Fujita intensity scale, an F0 is less than 72 miles per hour. We'll just do miles an hour. You get very light damage. This would be, if you're going to see a tornado, this would probably be the one if you were close by to see, because you could probably walk up to it and not die. But if you did an F1, things start to get a little scary. 72 miles an hour to 112, you get moderate damage. If you make it to an F2, it's 113 to 157 miles per hour with considerable damage. And F3 is a big deal. If you make it to an F4, you better be in a storm shelter or be somewhere safe, because this is devastating damage, because the winds get from 207 to 260 miles per hour. If you make it to an F5 and you've actually seen and witnessed an F5, you're in a rare club of people who witnessed this and lived to tell the story if you were actually in the storm itself. Winds greater than 260 miles an hour, and it's just incredibly devastating. Mass loss of property, life, and so forth. This is the worst kind of storm that can occur, and usually the most intense and eats the most material. So you have to assume the Fujita scale is really all about how much damage it occurs. How much does the tornado eat? So let's look at blue as the percentage of tornadoes that occur and measured by the Fujita, and pink is the percentage of deaths by the same measurement scale. You can see that most of our occurrence of tornadoes actually happen in the F0 and F1 categories. Then the next group would be F2 and F3. Look how rare an F4 and an F5 is. However, this particular bar right here indicates the loss of life. And you can see how much greater the loss of life is from an F0 and 1, F2 and 3 to an F4 and 5. When you look at by decade, what's happened since literally over the last, when we really first started issuing tornado warnings and trying to, that really started happening in this area is right around here, actually in the 70s. But you can see before we had a warning system in place how many deaths were associated with that. And it was a marker in this area right here that actually produced us to need to have a tornado warning system, which we'll learn about in a little bit. So if we added the last 3 decades into place from 1990 to 2000 to 2010, 2015 time frame, then you would see that that has stayed fairly consistent, if not even gone down a bit, because weather forecasting has improved for warning time to get people to safety. So let's move into hurricanes. These are really one of the most remarkable natural weather phenomena on the planet. They look much like a tornado, but they're much, much larger. These are the most violent storms on Earth, and in order to qualify as a hurricane, a couple of things must be met. The wind speeds must be in excess of 119 kilometers or 74 miles an hour. Again, we'll use the miles per hour. You must have rotation, that's a cyclone, and the typical profile of a hurricane ranges between latitudes of forming between 5 degrees north and south latitude to 20 degrees north and south latitude. That does not mean that may be where they end up, but that's where they originate, which is around the tropical area. And keep in mind, you've learned about the wind patterns and the wind belts. That's going to be in the tropical low depression area where we have that tropical low pressure system wind belt. So what do we call hurricanes? We call them typhoons in the Western Pacific. We call them cyclones in the Indian Ocean, willy willies in Australia. Interesting fact, I've been to Australia, that's what they really call them. An interesting thing to look at is the North Pacific has the greatest number per year, but you're thinking, well, I really know more about the Atlantic storms, which is what we call them in the Atlantic, or hurricanes. Gulf of Mexico and hurricanes has a high concentration of hurricanes, and we track them accordingly. So let's take a look at the profile of a hurricane. The typical profile is you'll have an eye wall. So the eye wall is actually one of the most dangerous parts of the hurricane itself because it's where the strongest winds are, it's the heaviest rainfall, the most devastating weather, and usually as the eye passes over, the backside is even worse than the front side. At least that's been my experience in the few hurricanes that I've lived through. You will see a massive concentration of cumulonimbus clouds. Look at this banding that occurs throughout the storm. The banding is very important in the rotation of a hurricane. At the very center, you get this eye. The size of the eye can vary. On average, they're about 12.5 miles in diameter. Precipitation ceases, you get fair weather, the winds die down, it looks like a hunky-dory, beautiful day to go play outside. Everybody likes to go outside after the first part of the hurricane hits to assess damage. Unfortunately, the worst is still probably yet to come when the backside of the storm comes through your neighborhood. And you can see as this one's moving on land, take a look at this red material right here. So if you, let's say you lived right here and the eye is passing over, you got some pretty nasty stuff coming your way for quite a while. So when you look at the cross-section of a hurricane, notice that you get constant rotation, much like a tornado, and you get these outflow, which creates banding, and the banding are these large arms of the hurricane. These spiral bounds are, or bands that are make these storms enormous and extremely dangerous, because anywhere in this system at any time you could produce something like a tornado, a big giant supercell, because you have to imagine a hurricane is a just supercell times 10, except it's forming over the ocean where you got warm water. So what's the profile in terms of wind speeds? Literally you're looking at they can reach speeds up to 300 kilometers per hour. They can generate wind-generated waves, that is, up to 50 feet at sea, but your worst and most dangerous part of a hurricane, besides all the wind, all the rain, is really storm surge. Storm surge is where that ocean has being pushed by the wind and literally pushes a wall of water onto land. So the flatter the land, the more at risk you are for storm surge. Hurricanes form and they dissipate in tropical waters, except in the South Atlantic and the eastern South Pacific. So let's take a look at Hurricane Ike. Everybody remembers that from 2008. It actually starts to look right here. You see the formation of, they issued a hurricane warning in this area, and literally 8 a.m. the next day, 8 a.m. on Wednesday, 8 a.m. on Thursday, 8 a.m. on Friday, and you can see that Ike went right where they said it was going to go. My sister lives in Houston, and she lives inside the loop, the 610 loop, because she works downtown. And she said after Hurricane Rita, nobody really took Ike very seriously and decided to stay put since everyone tried to evacuate with Hurricane Rita, and it caused one of the biggest evacuation disasters in the history of the United States. So most of us said, oh, we'll just wait it out and we'll have Ike parties. Well, they did, and it was devastating because the storm hit smack dead on to Houston, Texas, and Galveston. And they were at her work building. She works in a real tall building. She's an attorney there. And it knocked out a bunch of their windows. And she said it was really scary because we could feel the building sway. And these are the kinds of things that you need to really consider when a hurricane warning's been issued for your area. Evacuate. Even if you're not worried about your life, worry about the people's lives who will have to come in and rescue you if you don't get out in time. And those would be the emergency management people. So that was one of the stories of Hurricane Ike that was so devastating, was people didn't take these warnings very seriously, especially at the Galveston area. And a number of people had to risk their lives, and some lost them, to save the people who decided to stay behind because they didn't want to take the warnings seriously. So where does the energy come for hurricane? It comes from that latent heat of condensation. Remember learning about that earlier on in meteorology? That's that hidden heat, that's that transfer of heat going from one type of solid to a liquid, liquid to a solid, vapor, solid, back and forth, those rotations of the energy stored in water. Typically, hurricanes form in the late summer because the warmer water temperatures of the ocean have reached their peak, and so you get extra bonus points for latent heat of condensation. So as those storms approach land, they don't have as much energy to pull from, so they lose in kind of their gustiness, their robustness, and they fizzle out on land. So let's look at Hurricane Katrina, and I want you to track kind of looking at where she went. And while we tracked her over the Gulf of Mexico, here's the coastline of Texas, New Orleans, Mississippi. And initially, this thing, had crossed over Florida. We'll talk a little bit more about it shortly, but it gained a lot of strength right in here. Why it gained strength was because of latent heat of condensation. I keep saying that term, so it's important enough for you to know for a test. A hurricane gains strength because of latent heat of condensation. So this was Katrina at the Saffir-Simpson at a Category 5, and when she reached a Category 5, look at this well-defined storm. You can really see the spirals and the eye wall, and she made landfall right in this area, right in here. So you hear a lot about New Orleans. So we're going to show you some photos from Mississippi. It'll blow your socks off if you didn't really follow that, because it was devastating impacts. We'll talk more about that shortly. Now, the hurricane that same year that was so devastating to Texas was Hurricane Rita. While Hurricane Katrina was thought to kind of made it to Texas, it didn't reach us. It hit New Orleans and Mississippi, but Hurricane Rita was thought to hit dead on at Houston, Texas. Instead, it hit a little bit further north and impacted areas like Tyler and Sabine River Basin, Beaumont, those regions. I can remember working for the Texas Commission on Environmental Quality that year, and our emergency response team had already been deployed to help out with the cleanup of Hurricane Katrina. And when Hurricane Rita hit, it shut down a number of our TCEQ offices that were along the coastline areas, including Tyler, for multiple weeks until the flooding could be fixed. Hurricane Rita was a stronger storm than Katrina. There was even a stronger storm than both of those that same year, Hurricane Wilma. And we'll be looking at all three of those here shortly. When does a hurricane form? What are the stages it forms in? If you get a tropical depression, winds do not exceed 38 miles per hour. So they reach up to 37 miles an hour. If you get a tropical storm, by the way, a tropical storm is when a storm gets named. A depression only has a number associated with it. These go from 38 to 73 miles per hour. I've endured both a tropical depression and part of a tropical storm. I was able to get out of a tropical storm area, but I was on an island, a very tiny island, for a tropical depression. This is not something I want to redo in my lifetime. I've also endured a hurricane, several of them, when I lived in Houston, and one of them ate our boat, and one of them, the same one, put a pine tree through my bedroom, and I will never forget that. Those were things that damage to our house, and we were a long way from the coastline. So that was probably the time I realized how devastating a hurricane can be. If you make it to a hurricane, it's 74 miles an hour plus. There are 5 levels of hurricane categories. So for your test, you're going to need to know the wind speeds for tropical depressions, tropical storms, and hurricanes. So let's look at the Saffir-Simpson scale. Minor damage occurs on a 74 to 95 mile per hour. Having said that, you can get substantially dangerous winds even at 74 miles an hour. If you make it to a moderate Category 2 storm, the winds go from 96 to 110 miles per hour. If you make it to a 3, you'll get major damage, and wind speeds are 111 miles per hour to 130 miles an hour. And you make it to a Category 4 storm, kind of like on the tornado Fujita scale. This is an extremely serious and devastating event, 131 to 155 miles per hour. If you reach a Category 5 storm, it's wide open, anything greater than 155 miles an hour. So I would also correlate something here. If you were to see a storm and it was, let's say, a 3 and it quickly becomes a 4 and Category 5, typically what's happened is the millibar readings have dropped, so the pressure system's dropped, and it's become and picked up more energy from latent heat of condensation. So where they move, as they diminish their strength, either they come across cooler waters in the ocean or they come on the land and can't get that latent heat of condensation. So once that happens and it comes onto land, what will happen is it will usually fizzle out for a while. Let's say, for example, Tropical Storm Allison came into Houston, Texas back in 2001 and fizzled out right about here and dropped over 30 inches of rain in just a few days. Flooded out the inner section of Houston, like the Loop, all of downtown. And that was a precursor to how do we deal with something like Hurricane Katrina. Because we actually had a major cleanup that was very similar to what Katrina had, almost identical on a smaller scale. And so we had practice with emergency response, and that's kind of what set emergency response into motion back in 2001 to make sure that we could have interpreparedness between intergovernmental agencies, cities, counties, emergency personnel from federal, state, local governments. How do we coordinate to get food in, water in? How do we get people out? What do you do with all the hazardous waste? What do you do with all the uprooted petroleum storage tanks? This is things you don't really think about, but realities of these types of storms. So this was destruction from a hurricane, not a tornado, and I want you just to notice what's left or what's not left. First of all, I need to kind of be blunt. This area had both anchored structures like regular houses that weren't anchored down to a foundation, and then of course mobile homes. If you have a mobile home and there's a hurricane or a tornado coming, you need to leave your belongings behind. Get your dog, your cat, your kids, yourself, get out of there. It's an unsafe place to be during one of these storms. So obviously the strength of the storm has a massive impact as to what kind of damage can be done. Amount of storm surge that comes in would be number 2. How populated is an area? What kind of structures are there? How are they built? Probably one of the most important factors is the shape of the ocean bottom, because the flatter and the less dip that it has geologically, if it's really flat like this, a low grade, storm surge can just push right in. It doesn't have any resistance or much friction, so it floods a deeper and further inland area. And that's certainly been the case for a number of hurricanes that have hit along the Atlantic and Gulf of Mexico regions. So this is the kind of damage that a hurricane does. Looking at satellite damage here, I want you to notice it relocated an entire beach line. So that's one of the problems. We already have problems with longshore drift that you learned about and longshore currents from oceanography, but when you get a hurricane, you can redecorate an entire coastline depending on the strength of that hurricane. Let's talk about the infamous hurricane that actually led to the formation of the Saffir-Simpson scale. Let's talk about how the Saffir-Simpson scale got developed. Herbert Saffir was actually an engineer that had been hired by the United Nations to study hurricane-prone areas and how to get damages to those areas, planning for these types of storms when they happened. And he realized there really wasn't a good scale put in place in order to have a comparison of record like we have, for example, earthquakes for Richter scale. So he worked with another gentleman who at the time worked for the National Hurricane Center, and they developed a scale that was in relationship to this particular hurricane, where this particular modeling and warning system was used for the very first time. In 1969, Hurricane Camille produced the largest storm surge on record that had ever happened to that date. And this warning system helped save lives, where some calls were made to say, hey, this is going to be an area where the storm surge is going to be super prone to causing massive loss of lives and property. Evacuate these people. And so that's exactly what happened. And that's when the need for the Saffir-Simpson scale became a reality. So hurricane names are chosen every year, and there's a list for 6 years in a row. And there's a backup list, as a matter of fact. In the year of Hurricane Katrina and Rita, they had to go to the backup list. This is managed by the World Meteorological Organization, and every 6th year the list starts over again. Starting in 1979, both male and female names were rotated, and so you may not recognize anyone on this list right here. You could choose the list for the current year that we're in and see if any of them match this list, but this is just one of the 6 lists that are in place for the Atlantic Ocean Basin. Sometimes hurricane names get retired, and they deserve to be retired. When you get something as powerful as the ones that you see right here, you can begin to understand the reasons for them being retired. When you look at Hurricane Alicia, it says North Texas. Well, that impacted Houston, and that's where the one that hurt my house and took my boat. Hurricane Allison, or should I say Tropical Storm Allison, it wasn't even a hurricane. Tropical Storm Allison was so devastating in 2001 that it did so much damage and loss of property and life in Houston, it got taken off the list. If you haven't heard about some of these, let's talk about one of the ones you should know, which is Ike, Katrina, Rita, and if you didn't remember Wilma, it all happened in the same hurricane year as Katrina. These were some absolutely crazy, devastating storms. To not be as confusing for insurance claims, for court cases, and out of respect for people who lost their lives, properties, and families in these storms, some of these names are permanently retired. All right, so let's take a break and we'll come back and see more for weather disasters after the break. I'll see you in a few minutes. Bye.